Okay, so up until last week, we've gone over the concepts of Gaussian mixture model and fitting them using the EM algorithm. A critical point of implementing a Gaussian mixture model for any given data set is to figure out what is going to be the number of clusters or classes or components or populations in our model, right? So we were in a situation that if we suppose that we have either univariate or multivariate observations, x1 up to xn, and our goal is to cluster these observations using a Gaussian mixture model, then we have a PDF of any given data point being able to be written as this mixture where we are choosing a particular choice of C, right? We're fixing that choice. Now, we're fixing that choice maybe by some prior knowledge that we might have on what type of number of clusters does this population exhibit. But in many cases, we have no idea on the type of clusters that we expect and the different number of clusters that we expect. So the question is, how do we actually end up choosing C? How do you choose C, right? Should C be 2? Should C be 3? Should C be 4? Are there no clusters, as in C1, that all of the data is from one Gaussian? Now, recall that the way we're fitting these models is by using the log likelihood, right? So we see in general, the log likelihood tells us, given a certain values of the parameter, what values of the parameter, sorry, are most likely given the data that we have observed, right? This is what we know log likelihood to be, which means that we also know that a larger value of the log likelihood means a better model. So if we have a log likelihood that looks like this, I know the value that gives me this value of the log likelihood is significantly better than this particular value that gives me this log likelihood. Okay, so larger values of the log likelihood are better. So thus, in principle, we should be able to use the negative log likelihood to see how bad our estimates are, right? Or the positive log likelihood, maximize the positive log likelihood. But the issue is in choosing the number of clusters C. So when we have a fixed C, we can use the log likelihood to find the estimates of the vector of mu's and sigmas and pi's. Okay, but the negative log likelihood will keep reducing always as C increases. This is because, so that what I'm saying is that as C increases, our log likelihood value will keep changing and keep increasing, or more significantly, the negative log likelihood, or equivalently, sorry, the negative log likelihood value will keep decreasing. Now, the choice of C, sorry, now why would the value of C keep reducing the negative log likelihood? Why would, as C increases, would I get better and better log likelihood values or worse negative log likelihood values? And the reason is the following, that if I have data that looks something like this, let's say in a two-dimensional grid, right? So we have two dimensions, x1, x2, and we have data like this. And I want to mark it in two clusters, for example. Then two clusters might look like, something like this. Okay? If I want to mark it in three clusters, it might look something like this. And if I want to mark it in four clusters, it might look something like this, right? And so on and so forth. Now, what will happen is if I set the number of clusters C to be equal to n, which means that I say then the number of clusters is exactly equal to each sample data point, then what is going to happen is every cluster is going to be given its own singular data point. So this will be every cluster. And as it turns out, this cluster has zero variability because there's only one sample in each of the clusters. Further, every data point fits its clusters perfectly because that one data point perfectly characterizes this cluster. This data point perfectly characterizes this cluster and so on. Okay, so here's what's going to happen. So as C increases, the negative log likelihood will generally keep on reducing since each data point will want to be in its own cluster. Thus, the number of clusters that will give the best log likelihood value will be C equals N. And this is obviously not going to be a good choice for us. We are not interested in clustering that give every data point is its own cluster, because then we're not learning anything, we're not finding any trends, and we're not going to be able to use that clustering for, let's say, prediction or classification or clustering in a completely new problem. Okay? So clearly, just using the log likelihood value is not going to get us anywhere. Instead, a model selection procedure that's very popular could be used, and that's called the Bayesian information criteria. And the idea is the following, that for a given choice of C, you take the you take the log likelihood, and you say, okay, log likelihood value is good. I know I want to increase the log likelihood value, but I want to make sure I penalize the increase in the log likelihood if I am trying to fit too many clusters. If the number of clusters are too many, then I want to penalize that. Okay, so the BIC, or the Bayesian information criteria, is a function of the log likelihood and a penalty term that penalizes the number of parameters the algorithm has to estimate K. So every parameter, in every model, there's going to be a number of parameters it's estimating. For example, here I'm estimating, I'm estimating all the mu1, mu2 up to mu c. If it's univariate, and then sigma 1 squared, sigma 2 squared up to sigma squared c, and also, pi 1, pi 2 up to pi c minus 1. So that's going to be a lot of parameters. And as you increase C, that number of parameters will keep on increasing. Okay. So if C increases, the number of parameters to be estimated increases, and a larger penalty is imposed. So the BIC criteria itself is 2 log likelihood minus log n times K. Now sometimes, I just want to write this down, sometimes BIC is actually, more often BIC is 2 log likelihood minus 2 log likelihood theta given x plus log nk. So sometimes it's basically the negative of what I've given you here, in which case we want to minimize the BIC rather than maximizing the BIC. But I'm focusing often on maximizing things, so I'm only talking about maximizing here. Okay, so the BIC is 2 times the log likelihood, so that's good, minus log n times k. So if I increase the number of clusters C, then this is going to increase, but then this part is going to decrease, right? This part, this positive part increases as well, which overall decreases the BIC. Why does this part increase? This part increases because as C increases, the number of parameters in K increases as well. Okay, so increasing number of clusters is going to naturally increase the log likelihood, but also increase this term, making the BIC potentially smaller. Okay, so there will be some increasing value of C, the clusters, where the increase in this is significant than the penalty imposed by the number of components introduced. So idea is that the increase in log likelihood should be justified. And only then is BIC going to, only then do we want to choose that number of clusters C. Otherwise, we don't want to choose those number of clusters C. Okay. Okay. And so the BIC decreases when the number of clusters increases for large data. This makes sense, since when large number of data are available, we should be able to find simpler models. And this point is trying to indicate that the penalty term has a factor of n in here, which means if I have a large amount of data, then I want to penalize more and more, because if I have more data, then I should be able to find the simpler trends, the simpler models. Okay. And in general, this is the big note, is we want to choose C such that the value of BIC is maximized. If we were looking at this definition of BIC, then we would want to minimize it. But with the definition we have indicated, we want to maximize it. Okay. Okay, so now what I'm going to do in the rest of the lecture video here is go through the act of implementing the EM algorithm with the Gaussian mixture model for the Old Faithful data set, but using and actually not fixing the number of clusters C, but choosing the number of clusters C. So recall that we've already gone through the multivariate Gaussian mixture code. So over here we call the multivariate norm library, MVT library. And then we write up a function that calculates a log likelihood. This will be used later. Okay. Then we make a function that's GMM for D, which actually implements our Gaussian mixture model, right, for a given data set X, right? So it calculates the parameters, the N and P. It gives starting values, your starting values for pi's, mu's, and sigma. And then the EAM algorithm iterates basically by finding your E step, which is you're finding your gamma ICKs, and then updates your M step, which means you get your update for pi's, you get your update for sigmas, and you get your updates for mu's as well over here. Okay, so this is something we've already gone through in the previous video last week. This is exactly the same code. The difference is that this function, recall, has in its argument the number of clusters C I want to input as well. So previously we only implemented C equals 2, but now we're going to start implementing other number of clusters C, and the code adapts to that. Okay. So recall that we did the following fit. We also fit a 2-cluster model for the old geezer data set. So we load the data set, we set C to 2, and then we fit 4 different models. Now the reason we had fit 4 different models or 4 different versions was because I know that every time I run this, because I'm starting from random starting values, my algorithm can convert to local maximas. And where it converges to may not be a global maxima, which means that I'm going to run it for different starting values every single time and look at where we have converged. And we're going to see that this converges to not just one solution. All 4 of them will not agree all the time on the actual optimum. And how do we figure out which optima is better than the other optima? Well, we figure it out using the log likelihood. Okay, so this is what we had seen, that this is, we see our 4 different fits. This was our data set. So we have the first component of the faithful, second component of the faithful data set. So this is eruption time, this is waiting time. And what we did last time as well, is we color coded the data, the observations based on the class or the component it landed in from the gamma ICK probabilities. And then also made a shape of the Gaussian distribution covariance matrix as arising from these 2 fitted cluster distributions. Also, as type of part of the header, I put in the final log likelihood value. Now we see that these 3 are exactly the same fits, but the second model over here gives me a very different log likelihood value and very different clustering from the other 3, right? But I know this one, and I discussed in the last time, this one is a local maxima. I know this because the log likelihood value is less than the other model's log likelihood value. So I can pick up any of this, or this to be the better fit. Okay, so this is something we had already done, right? But now what we want to do is we're actually trying to see, is C equals 2 good or is something else better? Okay. So we're gonna start doing this. So the question is, are 2 clusters good enough, or do 3 or more clusters make more sense? So I'm going to fit this for C equals 2, 3, and 4. Now we can continue and keep doing it for 5 and 6, but it will be clear that that's not going to be very fruitful. But what first I do is, remember in the BIC, I have 2 log likelihood minus log NK. And this K is something I need to know. Now, what is k? So first I'm going to make a function that finds the number of parameters I'm estimating k. Now, what is k? Well, in this example, note that I have c minus 1 pi's. I have c times p of the mu's that I'm estimating. And the sigma covariance matrix is a p by p covariance matrix. Now, in a p by p covariance matrix, okay, so this is sigma. I am estimating all the diagonals, right? So that's p of the diagonals, plus I'm estimating all the off diagonals, right? I'm estimating all the off diagonals. But this off diagonal is exactly the same as this off diagonal because it's a symmetric matrix. So I actually don't need to estimate the downstairs diagonal because that's redundant, that if I can estimate the upstairs diagonal, it's exactly the same as the downstairs diagonal. So how many elements am I estimating? Well, I have overall p squared elements in my matrix, okay? And what I only want to take the upper diagonal, and I want to take the actual diagonal. So if I have p squared elements in my matrix, let me take away p elements from them, which means I've taken away my diagonal. So I only get, this. Right? So p squared minus p is this and this, right? And then I'm going to divide it by 2 to only get this part. And then I'm going to add p. Okay? And when I do this, this is p times p plus 1 by 2. So this means that in every sigma covariance matrix, there are p times p plus 1 by 2 number of components in each cluster. So the final number of parameters in K is Cp plus C times p plus 1 by 2 plus C minus 1. These are the total number of parameters in the model fit. And I make a function K par. Okay, now that I've done that, I've understood what's happening there. Now I can go ahead and fit C equals 3 and 4. Now the function that I've written, I don't need to do anything new, anything different. I can just call it for C equals 3 and I'm good to go. Okay. Now the only thing over here is, notice I fit 6 models, and the reason I fit 6 of them and not 4 is because as C increases, I'm going to start seeing more and more local maximas happening. So I just want to do a slightly more exhaustive search, so I fit 6 models. Okay. And as I fit them, I don't know how to know which one's better than the other, but in a 2-dimensional implementation, I can actually visualize this. So I make my plot again using the chunk of code that's all shared with you. I can make the plot, and this is what I get. This is for model 1, model 2, model 3, 4, 5, and 6. Okay. Now, what we notice actually is the first 5 of them are exactly the same models. So that's good, right? The last one, though, is a different model, right? Now, the first 5 of them look very interesting. There's one clustering here, one clustering here, one clustering here. So in the previous, when C equals 2, it was this and this. That was the best clustering. Now here we have one option that's this, this, and this, and that's all 5 of them. And then I have one option that's this, this, and interestingly, this. Okay, so what's happening is, it looks like the second cluster that we had before has a cluster within it that's significantly different, maybe from the inside cluster. And as it turns out, that this log likelihood value is greater than this log likelihood value. So this is our chosen cluster, right? It looks weird, but this is the one that the algorithm thinks has a better likelihood value. Okay, so that's done. But we're going to do this. So model 6 is the above best log likelihood. So that will be the chosen model. And now we do this again for C equals 4. Now the reason I'm not doing this live in front of you in R is because this code takes time. And so that's why I'm showing you the output and not actually doing this in our studio, because it takes me, sometimes 3-4 minutes for this algorithms to run. I will say that you can code the EM algorithm very efficiently. The code that I've shared with you is code that's easy to read for you to understand the logic. And that's the reason why I've written it that way. Okay, so now I do this again for C equals 4. Again, I fit 6 of these models. Okay, 6 again, so that I can allow each run to converge at a different local maxima, and then I'll have different options to choose from potentially. And once I do this, again, I'm going to start looking at the final fits. Now, again, I see something different going on. I see one fit here. This is a different fit. I can see just by the log likelihood. Again, a third different fit. This is the same as before. This is the same as before. This is the same as before. So I see 3 unique different fits in models 1, 2, 3. And the one with the best log likelihood value, the largest log likelihood value is this. So I'm going to choose model 1 over here, right? So I had this as an option, which is interesting. This is an option which finds different data, different subset here, but then I choose this, which is interesting also because it sort of retains this structure, this structure, this structure when C equals 3, but then adds a new covariant structure, new cluster within that structure, which is quite interesting. So and that just includes, the terms in the middle over here. Okay. And so model 1 in this case is my chosen model. So model 1 is the largest log likelihood. Now, again, I want to stress that note that there is no guarantee that the solution we have converged to here, in this case, model 1, is in fact the global maximum. We don't know it. We know it is the best amongst the ones we implemented, but we're not sure if it's the global maxima or not. Okay, model 1, not model 5. Model 1 could still be a local maxima, and there could be another model out there that is better. We may need to run the function a few more times to see if the model fit converges to some other solution and see whether anything works better. In this case, we ran it 6 different runs. Seems to work, but we can't take anything for guarantee. Okay, so at this point, we have run this for C equals 2, 3, and 4, and in each of those runs found the best model fit. But that is the best model fit for C equals 2, C equals 3, C equals 4. I don't know yet which one to choose, this one, or this one. And that's where I use BIC. Because in BIC, I go to my chosen models. So the first model in C equals 2, the sixth model in C equals 3, and the first model in C equals 4. And then I do 2 times its log likelihood, which was returned as part of my function, minus log n times k, which is calculated using this, minus log n times k minus log n times k, where n is the number of data points in my data, which is from here. Okay. And I calculate this in BIC.2, BIC.3, BIC.4, and when I print it, I see that these are the 3 BIC values. I see this, and I see this. And as it turns out that this one is the largest BIC value, so which means that C equals 2 gives me the largest and the best BIC value, and thus in that case we will choose 2 clusters in this particular data set, right? And that's what we will end up choosing. So that's the takeaway after you've implemented BIC, right? Okay. Now we can see also from the model fit that C equals 4 did seem a little stretched in the sense that I'm not sure that there's a need to actually fit 4 clusters in here. And I can see from C equals 3 that this one looks maybe not as good as, and not as easy to see and not as interpretable and useful in practice as our C equals 2 clustering, which is very simple to recognize and see. Right? So BIC helps us go to reasonable, more parsimonious meaning simpler classifications, simple clustering, and that allows us to actually take our model fits outside our particular data set and potentially generalize in other different situations. If we go for too complex clustering, then that's not going to be able to generalize outside of the data set we're working with. And so we want to stick to simpler models, and BIC, because of the penalty term, allows us to do that.